Richa? Hi, Richa. Sorry you couldn't be with us, but wow, are you missing a fun day? We're going to do cylindrical shells, another way to find volumes of revolution. Look, this is not required on the AP exam. That being said, a friend of mine actually teaches other teachers how to prepare for the AP exam, having taught many, many years himself. And he said in his class to everyone, look, even though this is not an official topic on the AP exam, please learn it all the same. Make sure that your students know it. Here's why. There are some problems where you might have to do more work. And I think we saw that yesterday doing number 18, I believe, just setting it up one another up on the whiteboard. But this will give you an optional way to do a volume. Cylindrical shells, the big difference, I've highlighted that in green. Rectangles are parallel to the rotated axis. And for some solids, it's more convenient, it's easier to use shells. So let's say we've got this region right here that I'm touching. Let's make a revolution about the y-axis. Let's build a rectangle that would be parallel to the y-axis, not perpendicular to it. If it was perpendicular, we'd need the washer method, wouldn't we? Because of that additional space. But as we envision this being revolved around, you could rotate this little rectangle around, and of course you would get this cylindrical shell that you would see in letter C here. If we were to slice that open and unravel it, where I'm touching right here, you get this rectangular prism. I've highlighted in yellow here the face of that rectangle that would be originally formed. That rectangle would have a base of delta x, the height of fw sub k, and then you'd have the distance between the bases. We call that the height. You can see off to the side, the volume of a prism is always the area of the base times the height. This height, though, if you're revolving this around in that cylindrical shape, it's like unraveling a paper towel roll here. You wrap that around in a circular motion. That height, the distance around, is the circumference that we get going about. So we'd have 2 pi times w sub k. W sub k would be that arbitrary x value. So all of a sudden we look at this and we'd say, well, wow, that's a nice way to find a volume. Now that being said, if you were to add up a whole bunch of those, you should be able to get a volume of revolution. Now our textbook doesn't have the following representation, but I definitely want to point it out to you. The author says right here, that the volume is the integral from a to b, 2 pi x f of x dx. And sometimes kids look at that, and that is fine. That's what our textbook has. But I'd like to suggest to you a more comprehensive setup. In baseball and in softball, you might have heard of the designated hitter, the DH. And when we're doing cylindrical shells, I always remind kids of the DH. We're going to integrate from a to b of 2 pi. The D stands for the distance a rectangle is from the axis. The distance, an arbitrary rectangle, is from the axis of revolution. To find distance, it's always top minus bottom, or right minus left. The H stands for height, namely the height of a rectangle. And guys, if you work that out, you're going to find the volume of that rectangular prism, like we just said up above. Add up a whole bunch of them, an infinite number of them, in fact, and you will have your volume of revolution. So even though our author doesn't use that distance and height, I really think it's a super important, helpful way to see the problem. Quite honestly, if we don't think of it this way, later problems become very confusing. So even though what I'm circling right here is what the author has said, I think that this alternate form with the D and the H is far more helpful. So with no further ado, let's go ahead and try to do a problem with cylindrical shells. Let's say we've got y equals x squared. Of course, we've got this right over here. That's a parabola that's going to be opening upwards. Y squared equals 8x, or another way to look at that would be x equals y squared over 8 if you'd rather. What kind of a shape is that? A parabola opening what direction? To the right. And you might guess that we're still centered, at the origin. In fact, we are. And guys, it wouldn't take you too long, I hope, to be able to see that this is in fact the region that we have. This region is enclosed by these two parabolas, and we're going to revolve around the y-axis, of course, and that's going to be coming this way. You've done problems like this a lot. You've done quite a few of these over the last few days, and I hope that's no big deal. But we are about to look at things from a much different perspective. We're going to say, oh my goodness, perhaps we could look at this from shells, where your rectangles are not perpendicular to the axis, but parallel. I'm going to draw such a rectangle right now. That would be a rectangle that would be parallel to the y-axis. And just looking at that, you could draw another rectangle or two or three if you'd like. But regardless, we'd be stacking this rectangle in what direction? Left to right or up or down? What do you think? Left to right, meaning that we're going to integrate with respect to x. That's super, super, super important. So I can say, well, I'm going to use shells. I'm going to have dx here. I'm going to have 2 pi, and we're going to have distance, and we're going to have height. That's the designated hitter rule. And of course, we need bounds. We need boundaries here. Guess what our beginning x value is in this problem? It would be 0. We'd get 0 right here. And then, of course, we could say, well, my word, where might we be crossing? Where do you think we could be intersecting those two curves? You could solve algebraically, of course. You could set y equals x squared and plug that in and work it out. Or we can solve by inspection. Sometimes solving by inspection is so much easier. Could these two parabolas cross when x is equal to 1, do you think? No, because the first parabola would have the point 1, comma 1. The second one definitely would not. It would have 1, comma, and then y would be plus or minus the square root of 8. Might x equal 2 work? It does. You see, if I were to plug in a 2 up here, plug in a 2, 2 squared is 4. I'd have y is 4 when x is 2. Guys, if you were to plug in x equals 2 into that sideways parabola, you'd get 4 also. Yes? Yes. Okay? So, guys, at this point then, I'm going to be integrating from 0 to, what do you think? 2. So, I hope that much is making sense. We're going to build rectangles from x equals 0 up to x equals 2. But now we're going to say distance. How far is this rectangle from the axis of revolution? Wow. Tell you what, you could envision right here is your distance. And sometimes that can look a little strange. You could say, wow, how far is that? I guess what I want to point out to you, and this is going to be helpful for later problems, this rectangle would be defined for some w sub k. Now, the w sub k is really some arbitrary x value. In other words, there will be a rectangle drawn in when x is 1. And when x is 1.1, and when x is 1.375, and so forth. So you could envision, well, if this rectangle was drawn where x is equal to 1, would you agree we'd be one step away from the axis of revolution? So we're going to see that this will be a rectangle defined at x, and I'm going to say my y-axis is really x equals 0. I could call that x minus 0. I always want to confirm right minus left or top minus bottom to help you out. Yes?
Where'd the 0 come from?
The 0 comes from the y-axis right here from where I'm revolving around. That's the line x equals 0. Okay? Yes?
How about the x? I don't understand why you put x.
Well, I've got this rectangle right here, and it's drawn in for some x value. Right?
So you didn't, okay.
So I could say whatever, let's pretend it was drawn in at x equals 1.3. That was your w sub k, right? That would be your whatever x value I'm using to determine heights, right?
Okay.
So at that point, you could say, well, how far, let's just pretend it was at 1, how far would we be with an x value of 1 from that axis? It would be right minus left, whatever that x value is.
Okay.
Minus
so x is
0.
just an arbitrary number and it's not the problem.
Yeah,
Okay.
and x, Christina, very importantly, is going to pertain to building rectangles from 0 to 2. That's what the bounds are saying. And we're going to envision it being drawn for every x value, so to speak.
Okay.
And remember, those bases get to be super, super thin and super tiny, right?
Okay.
All right. So if we think about it that way, then we'll say, well, what about the height? Now, the height, please be careful. We need to have everything in terms of x. Everything has to be in terms of x. So we're going to do, for the height of this rectangle, top minus bottom. Top minus bottom. So the top, I think most kids would look at that and they'll say, well, it's this sideways parabola. The sideways parabola was y squared equals 8x, or x equals y squared over 8, either way. But think about that. If you had y squared equals 8x, how would I write that in terms of a function of x? Y equals the square root of 8x. It's plus or minus, right? Sometimes kids will be like, why can't you just write the y squared over 8? Well, I have a dx. I have to write everything with respect to x. And then guess what my bottom portion is? The bottom part of the rectangle is x squared. Now, guys, your distance and your height are not going to get squared. It's just that in and of itself. And believe it or not, this would get you the exact same answer as the washer method. And in fact, you can easily compare the washer method to this. You'd be like, wow, I'm getting the exact same thing. So let's talk about using the calculator and getting some help here. You know, you could most definitely just get this thing up and say, well, let's see, I'm going to go math and maybe bring up a 9. And I'm going to go from 0 all the way up to 2. You know, you could put pi in, but you don't have to. A lot of times I like to just put pi at the very end of the answer. And you'd say, well, the distance is x minus 0. I think we all know that's just an x. Inside here we'll have a radical 8x. You don't even have to simplify it, honestly. Minus x squared. And then we'll just put in our dx. And you just let this thing work out. You'll have to add a pi at the very end. It looks like about 4.7999, and you can ask the calculator if it could convert it to a decimal. Well, no, it won't. You could even multiply that by pi if you'd like, and get about 15.079. 15.079 would definitely be an okay answer. What else would be an okay answer? 4.799 pi. You could go either one of those. Okay, we doing all right? Okay, and like I said, the washer method would get you the exact same thing. So it looks like we're going to run out of time on the video, so we're going to have to look at other examples on a second video.